Looks like we're mostly complete, so I'll go ahead and get started. My name is Marco Esters. I'm a postdoc in Stefan Quadrarola's group and with the AFLOW team here. And I will go ahead and start talking about our database and our APIs that can be used to retrieve and filter our data. Big materials data repositories play a really important role in materials discovery, either for experimentalists or for computational materials scientists. They can inform experimentalists about which materials to synthesize, which ones may have interesting properties, and which ones may even be synthesizable, especially the latter will be addressed tomorrow by Dr. Aliases in a session about thermodynamic stability. And they can also be used to train machine learning models and train and validate data. So that's an interesting application for big data for computational materials scientists. And AFLOW is a very large database with over 3.5 million materials entries, and they are based on standardized ab initio calculations. So they're very helpful for these kind of purposes. And we have two ways to access our data. One is using a graphical user interface, and one is using application programming interfaces or APIs. And you already got to know one of our graphical user interfaces, which is our AFLOW search page. We got to play with it a little bit in the introduction, and that's where we will be picking off right now. So I would like everybody to go to aflow.org and go to the search page. So I'll go ahead and switch to my browser to demonstrate. Here we are, aflow.org. And here's the search page you already saw, that one in the introduction. So let's just start with something simple. Now let's start with a search for chromium containing properties in the ICSD catalog with three species. Just click on that drop-down menu here. If you were interested, for example, in something between 2 and 4 species, you can also switch to the range button. For now, we just want to stick to 3. And this starts the search. And we will end up with a list of compounds here because they're sorted alphabetically. It's mostly silver, chromium, and a chalcogen, some oxygen compounds, and here's some boron chromium alloys. And that's all fine, but let's make the search a little more complicated. Let's say we don't want any oxides. We're not interested in oxides. What you can do is use this operator keyboard here, if you will, and type in and not oxygen. You can also type this string out, but it's probably easier to just use the buttons. And we can search. And you see all the compounds that contain oxygen are all gone. We can make this query basically as complicated as we want, as complex as we want to. So let's say we want any kind of chromium compounds that contain selenium or tellurium, but also still chromium. And you can achieve that using these parentheses. This is the logical flow here, chromium and selenium or tellurium. As long as this is enclosed in parentheses, you will get the results you want. You can search again. And you see that we will get compounds that have either tellurium or selenium or maybe both and chromium, but you won't find anything that doesn't have any selenium or tellurium in it. We can scan through the pages just to show you there's always selenium or tellurium inside. You won't find anything that doesn't have either of them inside here. So this is how complicated your search query can become if you so choose. That itself is fine. You can see what kind of compounds we have in the database, but what most people are really interested in is actual properties. So let's start looking for one. To get there, you can click on this button here to get to the property filters, or if you prefer to have everything on one page, you can also just flip that slider here and you have the property filters and the periodic table all in one page. I personally prefer the compact look, but it's a matter of taste. So let's look for the so-called Vrh Bulk Modulus. What that is exactly will be explained tomorrow by Professor Cormac Tor in the session about thermomechanical properties. It's somewhere here in the mechanical properties tab, but if we don't want to keep looking through categories, we can also use that search field up there. Let's type in bulk, and here it is. This is the one that we are looking for, the Vrh Bulk Modulus, calculated using AEL, which Cormac will explain tomorrow. And let's renew our search. And you will see there's another property that was added. Here are all the entries, and here are the bulk moduli. Here in this column, we can sort by clicking on these carries. There's his sorted in ascending order and descending order. Like the one with the highest bulk modulus is the chromium tellurium oxide, and one with the lowest is silver chromium telluride. So now we found a compound that is potentially interesting and has a low bulk modulus with the elements that we want. So let's look at what else we can find for that property. Here's one of the links that you can click on, and that will get you to this materials page. You already saw that in one of the last sessions. After it's loaded, Dr. David Hicks explained the symmetry table here. It's a little cramped because I zoomed in a little bit more, but here's the JMOL structure viewer. But we have a lot more down here. There's structure here. We have a lot of symmetry here, the reciprocal lattice. Here we have some thermodynamic properties. We have beta charges, which is very useful if you want to look at charge distribution. We have magnetic properties. This one looks like is a magnetic compound with a with 0.8 4 magnetons per atom. It's metallic. You can see the band gap type is metallic, but you can also look at the band structure here. We have a little interactive band structure app, and some calculation details just in case you want to maybe reproduce our results, or you want to compare our calculation parameters with whatever you use, maybe see where differences in results are coming from. And here are a couple of downloadable files. Here's here's the postcard of the final structure that you can download, and K-points file, and the beta file. So the entry page contains basically the properties that we calculated for this particular compound. So with that, I want to jump in straight into some exercises about the search page. So let's go into your VD portal, and if you haven't done so yet, load the AFLOW module, and we're going to the desktop, day 2, and you see we have the directory 05 database AFLUX, and a PDF of all the slides that you will be seeing and more. And what you see in the exercises directory is a Jupyter notebook, and we're going to be using Jupyter throughout the rest of this session. To start it, you type Jupyter notebook, and then 5 AFLOW school database AFLUX IPy or just type in 5 and hit tab to autocomplete, and it will load in your VD portal in your browser. It will, after a little bit, it will start opening that notebook. So let's see. I need to see how I can zoom in here. Yeah, there you go. I hope that's big enough. And if you double click on band gap and these, you can actually edit them. But here are the the 3 exercises that I want you to do just to get warmed up a little bit about our search engine. Use the advanced search page and the ICSD catalog to find the band gap of manganese dibromide in a particular space group 164. And then I would like you to find the Vrh bulk moduli for materials containing titanium. You can check the one with the highest bulk modulus, so check out the one with the highest bulk modulus. Determine what the lattice type and the space group of this material is, and if it's a metal or an insulator. And at last, I would like you to find the Vrh shear moduli, not the bulk moduli, and find the one with the highest and the lowest shear modulus. So we can either, okay, getting back to the exercises, the first one was about finding the band gap of manganese bromide in space group 164. Let's go to the advanced search page and just set everything just to get a clean slate. And we want manganese bromide. So we click on manganese and on bromide. It will automatically assume and in between. So you don't have to type and all the time. And we need 2 species because it's only manganese and bromide. And we want the electronic band gap here. And we can restrict the space group if we want to 164 and 164. But if you search without restricting, you only get 3 results back. So it's pretty easy to see either way. And it's 3.38. We can also just unrestrict the space group and you will see there's not really all that much in there. The 3.39 might involve the space group 166. So they're very close, so it's easy to miss that. The second exercise, so we can write that down here, is 3.38 electron volts. The second one was to find the bulk moduli for materials containing titanium in the ICSD catalog. And for that, we will reset the search again, just to start clean slate. Bulk modulus, add that to the properties. And we are looking for titanium without any other restrictions, just bulk moduli titanium. And wait for the results to come back. And here we see all the bulk moduli. We can sort them, this button. And we see, as Josiah Anzimona correctly predicted or found, that it is iridium-3 titanium. And when we go onto the materials page, we can scroll down to ask for the lattice type. Browse that as primitive. It's cubic, so it's simple cubic. You can also see this if you know a little bit about crystallography when you look at the structure, that it is simple cubic. The space group, let's find it here, is 221 or PM3 bar M. And the type here, band gap type, is metal, or if you look at the band structure or the density of states here, it's pretty obvious that this is a metallic compound. So we have compound was iridium-3 titanium, lattice type was simple cubic, space group 221, metal or insulator, it's a metal. Then lastly, it was a little trickier. Finding the shear moduli for materials containing at least 1 halogen but no chalcogens in the ICSD catalog, and then sorting them. For that, let's reset the search again. We want the shear modulus, and now how do we select the properties? So we have these handy buttons here. We can use them just as easily as we can for any other elements, and we can sort. The lowest shear modulus is titanium tetrabromide, 0.65 gigapascal. So it is Vr4 Ti. Let's say 0.64 gigapascal. That's the lowest, not the highest. Or 6.5. And the highest, we just sorted descending. This is 80.89 gigapascal, and the compound is a magnesium 3, fluorine 3, nitrogen, so F3, Mg3N. At least for the materials in our database, you see it has a halogen and no chalcogen in there. And if you go through the search results here, you will see none of them should contain a chalcogen. None of them should. They should all contain a halogen, fluoride. You see a lot of fluorides here, some chloride, bromide, etc. Any questions about the search page so far? Should be fairly straightforward mostly, but feel free to ask any questions in the chat. Looks like a couple of you got the exercises right. Looks like there are no questions, so I will move on to, how does this come up with a particular composition? Say ABX3. That is a much more difficult question. I'm not sure if we can actually currently do that. It has the following problem. It will be difficult. It's difficult to implement this because ABX3 is kind of a reduced chemical formula. It will be a good feature to implement. Right now, our search page cannot make that specific of a guess, so that specific of a search. Because searching through arrays is actually not very trivial. So you would have to filter. You would have to find those manually. You can do this with the feature that I'm going to present to a certain extent. Right now on the search page, we unfortunately cannot have that kind of stoichiometry search. It's a good question, though. It's actually a difficult problem. Doesn't look like there are any more questions. So this having a graphical search page is nice, is fine, but it doesn't help us for any kind of high throughput application. So what we want, or what we would like, is to have some kind of program that allows us to do this kind of search, but do this programmatically, so we can have like a high throughput data filter through our database and put that, for example, into a Python script or any kind of programming language, so we can grab data, for example, for machine learning purposes. And for that, we have developed the so-called AFLUX search API. A search API essentially combines that search property with basically has the same search functionality as we have online, but we can actually access this programmatically. And the AFLUX search API has a certain call structure, and I will introduce this a little bit more, and we go through plenty of examples about what AFLUX can do. So it consists first of all of the server, which is aflow.org/API/AFLUX. And then it has, in the query portion of your URL, it has two different components. One is the so-called matchbook, and one is the so-called directive. We will go through both of these components, and I will introduce kind of exactly what these different components do. But in short, the matchbook is essentially the materials keywords with arguments. So what we did before, looking for the bulk modulus, we can narrow down the species. We could search for species. That is what the matchbook is for. And the keyword list is fairly long because we have a lot of properties. There is a help directive available that you can call this from, and I will demonstrate this a little bit later. And that's what you can use to really look at the properties that you're interested in. The directives are formatting directives. So how many results you get back. You may have noticed if you played a little more with the search page, the results are limited to about 1,000, to 1,000 entries. You can determine what kind of format you want things back. JSON is the default because a lot of programming languages, especially the ones that use machine learning, are based on Python. You also can return everything as an HTML table. And you can also control the number of results that you get back using the directives. So we will mostly, as I said, the AFLUX can be used in a Python script. Here's a minimal example. It needs JSON mostly, and the so-called URL request package for Python, because that one can actually create a URL. And most of the Jupyter notebook will use that kind of structure. So we have first our server, and then we will put the matchbook and the directives together. And then at the end, we will just submit a request to the server. You don't need Python for this. You can also just take a link and copy it into the browser. But with Jupyter, it's just easier to demonstrate what's going on. So let me go back and switch to Jupyter. So here is again the call structure, and this here is basically a minimal script that you need to actually query the AFLUX API. In this case, we will just use the help directive, and if you just click on this field and hit Control Enter, this executes the code. And what you see is what I do with every single thing that I will be doing in this session is it prints out the entire URL and the response. You see the response here is JSON. And it has AEL applied pressure, average external pressure. We see the bulk modulus ROIs that we get, that we got from the search page, folked the bulk modulus VRH. So you can take a look at all the properties in this help directive. And if you actually click on this link here that is printed out, you will see that you can do the same thing in a browser, but I'm using Jupyter because it's hard to zoom into this tiny part here of the browser. So if you're not familiar with Python, you can also make these requests in your browsers, and it will do the same thing. I recommend Firefox because Firefox has a nice JSON formatter in-house. AFLUX has certain operators. You saw already in the search page when we go back here that we have an and a not operator, and these operators are directly taken from AFLUX, and we have the same things here too. And we will go through the operators, and I will tell you kind of what they're doing. We have certain intra and operator scopes, so some that can be used only within a certain request, and some that can be used in between them. We have these bracket operators that are blocks. We have an AND operator, an OR operator, a NOT operator, and it looks like that this didn't really propagate. I'll fix this, but this should be, these are just the names. Looks like there's a version incompatibility between Jupyter that I use and the one here. There you are. We have an AND operator, OR, NOT, and a loose operator, string, and mute. That's it. And I will, in the next 30, 40 minutes or so, I will talk about what these operators are doing and how you can use those to form your AFLUX queries. We will use the following properties here in this tutorial. We have species, which you can use to filter down your species. We have the number of species that we had in the drop-down menu before. The catalog is the catalog of the entry. ICSD is what we use in our search page. We will look for band gaps, and we will look for spin of the atoms and some of the exercises. So let's start slowly, because the AFLUX syntax has a learning curve. So our first query was to search for compounds containing chromium in 3 species. That was the first thing we did when we did our search page search. So we will just build the matchbook. We will leave the directives alone. And when we're looking at how this is worded, we're looking for compounds containing chromium in 3 species. And the keyword, the property for that is species and N species. So species, chromium, because we're only looking for chromium, and N species is 3. Can everybody read it? Is that zoomed in enough? Can I get a thumbs up if that's big enough? Or do I need to zoom in more? Looks good. Okay, I get some thumbs ups. Excellent. So species is chromium because we're looking for chromium. N species is the keyword for the number of species. That's all we are doing right now. The final AFLUX request can be seen here, and it will take a little bit to do the request and load, especially if everybody is addressing the server. There it is. Forgot something. That's why it took so long. Shouldn't forget the ICSD catalog. Otherwise, it looks for through 3.5 million entries. So let's limit our search to the ICSD catalog. As we did before, and we get 862 results back. If we want to compare this to the AFLOW search page, if you remember, I can also just look again. We have 862 results. The first one here is silver chromium oxide, and here we also have silver chromium oxide. With the space group, the Pearson symbol, and the species. These are, along with the AUID and the AURL, default properties that you get returned. The AUID is a unique identifier for each entry that we have in the AFLOW database. And yeah, the compound name is also always returned. The AURL, I will explain in the end what that means. This is for our so-called REST API, and you will hear at the end what that's about. But this is how you essentially create a search with AFLUX. You need the API root, which is API/AFLUX. Then we have a matchbook, which consists of, here in this case, of our species search, the number of species in the catalog, and the directive is currently paging 1 format JSON. I will explain later what these directives mean exactly. That was a very simple search. Any questions about the call structure? Because the call structure is very important to understand before we move forward. Doesn't appear to be the case. So let's do a more complicated search. Just do the next search that we had in our example on the search page and exclude oxygen from the results. So we had species, chromium, and now we want to exclude oxygen and not oxygen. The not operator is the exclamation point. And we still have N species 3, and the catalog is ICSD. If you at some point, if you have trouble following along at some point, all these commands here that I'm typing, all these requests are in the PDF of or in the PDF that you have in your directory on day 2. So you can also start following along there a little bit. All these requests are available there. If you don't get the Jupyter commands, you can always look them up. But you can see that adding not oxygen, also the exclamation point oxygen, to your request removes a couple of entries. And for this one, the silver chromium oxide is not there anymore, just like what we had with the search page. I can show you in the search page that we get to the same number of results. If we exclude oxygen, we get 550 entries. Here we see we get entry 1 out of 550. The first entry is silver chromium sulfide. And here we also have silver chromium sulfide as the first entry, space group 160. Okay, let's do some more species searches. Again, ICSD catalog is ICSD, you can write that down. Number of species is 3, so N species 3. And species list, it says it contains chromium or manganese. And if we recall, the OR operator is the colon. It's chromium, colon, manganese. Let's start that search, either using Jupyter, or you can use this link here to get there. Just build that in your browser. You see we get 2,378 results. Here we have one with chromium. There's some more with chromium. At some point we should see one with manganese. There's one here. Silver, manganese, nitride. So we see that these entries will either contain manganese or chromium, and they're all going to be JSON formatted. The last one is going to be 3 species containing chromium and selenium, or chromium and tellurium. We had a similar request before. Let's do the common commands. So N species is 3 and catalog. It's ICSD. The species here we need to kind of put together. It says chromium and selenium, or chromium and tellurium. So we can use these parentheses to group logical groups. So chromium and selenium. And we also want chromium and tellurium. And these need to be connected with an OR operator. So chromium and selenium, or chromium and tellurium. You will see you get 115 back. You will see that all the results here with 3 species will either have chromium and selenium, or chromium and tellurium. It's also perfectly possible. Yes, I'll get to that in a second. Chromium or tellurium. It is of course also possible that you get just chromium, tellurium, and selenium. And Kamal just said in the chat that he did species chromium and selenium or tellurium, and it works the same way. That's because they are logically completely equivalent. Chromium and selenium, or chromium and tellurium, is the same as saying we want chromium and selenium or tellurium. There's definitely multiple ways how you can phrase a query like that. So we can show everybody the alternative solution to that problem, which is this here, and it gives you the exact same results back. Yes. Get 115 results. There's chromium, selenium, chromium, tellurium, silver, And if you go through them, you will see that there's always chromium and there's either selenium or tellurium inside. Whether or not you phrase it exactly the way it's phrased here, or if you use the equivalent alternative logical approach, it doesn't really matter. You can also flip any of them around, selenium and tellurium, you flip around, you can flip this to the front. It doesn't matter how you phrase it. As long as the logic is correct, you will get the correct result set. Yes, that's a good point. Any questions about how to piece those pieces together? You can see that the comma is used to add properties that you want to look for, and inside the species especially, you can use all kinds of logic to narrow down the compounds that you're interested in. If there are no more questions, then I will move on with our next operator. And we will talk about the loose operator now, which is the star. And let's say we want to retrieve the band gaps for all quaternary compounds in the AFLOW database. So we are using the property name egap, and we set n species to 4. Fairly simple request. We just said egap is the compound that we need. And we get something fairly surprising back. We get about 460,000 entries back, but we see egap being null. That means that we don't have a band gap calculated for this entry. We don't have band structure calculations for every single entry we have in the database because they're not cheap. But AFLUX will interpret this matchbook entry egap as okay, I'm getting a so there's a matchbook species chromium, oxygen doesn't work. So the query is this. Yes, it needs to have a comma, exactly. This comma needs to be there, otherwise it will not understand what you're talking about. The not operator refers to the oxygen, but AFLUX doesn't understand how to connect chromium and the not oxygen. So you need to add something in between here, either a comma if you want to say chromium and not oxygen, or an or. Chromium or not oxygen, whatever that would mean. But yeah, that's the big difference why this isn't working. Any more questions or problems? Undoing catalog, ACSD for the egap and species 4. Yes, this one here is not just, I can output the catalog too if you're interested. This one here is not just the ICSD. I'm using all of AFLOW because I'm trying to prove a point. Here, the catalog here is lib4. These are hypothetical compounds that are not in the ICSD database. It doesn't mean that they are unstable or anything. It just means that they're not in that particular database. So if you narrow this down to the ICSD catalog, you will indeed only get 8,885. But I would like you to not do the ICSD catalog because this one is what I'm trying to say doesn't work with the ICSD catalog because we have all the data, the band gaps calculated, or most of them calculated. So as you can see, egap here is null because AFLUX interprets adding egap just as return whatever value you have. And if we don't have that result, then it will just return null. That has multiple reasons. One is you may not want to exclude a result just because you don't have a band gap. So in order to force AFLUX to return the band gaps, you are using the so-called, you're going to use the so-called loose operator. So in parentheses, you use the star operator, the star here. And when you repeat your query, you will see you will get results back here. Most of the E gaps here are 0 because a lot of them are metals. But this is how you can tell AFLUX to return not null. And if you look at the AFLUX summons here that the search page does, we just want to add the bulk modulus. It does so automatically here in the search pages, adds that star operator. But for the API, you need to be a little more specific. So now let's, I already went a little ahead of myself here. So this is this returns null. And only showing non-null results requires the star operator here. So we can use the loose operator also to filter results. So let's say we are not interested in all the metals. Here are all the E gaps, they're all 0. We don't care because we want to look at semiconductors. So let's do again in species 4 and look for E gaps. So how do we filter? We can do the loose operator. We can use the loose operator to filter. In this case, we want any E gap greater than or equal to 1. And the way we write this is with 1 star. So the star comes after the 1. And this tells AFLUX to only look for band gaps that are 1 or above. And you can see here all the metals are gone from the results. You can do this the other way around too. And you can combine the two as well. And we will do this here. So let's look for band gaps that are 1 electron volt, that are between 1 electron volt and 3 electron volts. Again, in species 4. And the way we do this is, again, using the AND operator. So I already said greater than or equal to 1 is 1 star. The alternative is, so the opposite way, having it smaller than or equal to 3 is star 3. So you can kind of see what the loose operator does here. And we combine the two with the AND operator, and you will see in the end, returning everything here, that the E gap here is 1 at the first entry, and when we scroll all the way to the end, you see that the band gap, the last band gap, or the entry with the largest band gap of the set is 2.9998 electron volts. I guess we don't have anything that's exactly 3 electron volts, but this is how you can define a range between the band gap between your entries. You can do this with anything, not just E gap, but this is how you create a range to search for. So in this case, 1 star and star 3. Are there any questions about the loose operator? So again, to summarize, just using the star forces AFLUX to return only non-null results. So anything where we actually have the property available. Putting the loose operator right after a number means greater than or equal to. Putting a star in front of the number means smaller than or equal to. And constructing a query like this where we have number star, comma, star number means between these two numbers, between 1 and 3. These are the important filters, what you can use the star operator for. And you will get to play with that a little bit in the exercises later too. Okay, we said star means, okay. The question is star means greater than or equal to or the other way around. How would we do smaller than? Would 1 star and not 1 work? We can give that a try. Let's see. I'm actually not sure. I don't think we have this particular syntax implemented, and it's not 1. Yes, that's exactly what you could do. There used to be an entry where egaps what it was exactly 1. I can do this again. Here egap is 1, 6, 4, 2, 9 results, and not 1. Will return. The next one is 1.003. Yeah, it's very good, very good idea, very good question. Any other questions or yeah, any questions about either loose operator or how we can do a certain query? Doesn't appear to be the case. Then I will go to some more operators that the string operator is a little bit of a. It's important for certain applications. Let's take, for example, this AUID here. Let's say we want to return something about this particular compound. So we're looking for AUID, and we use AFLOW colon and that AUID from any of these entries. And if I try this, it's not going to work. It will not return anything. And the reason for that is that AFLOW thinks this here is an OR operator. So it's trying to look for an AUID that's either AFLOW or this hexadecimal number here. And for these kind of ambiguous problems, you use the single quotes. So whenever you have an AFLUX operator, he can actually get a result back. You need to surround it with single quotes. It's that's I think the biggest use for the single quote operator. The mute operator is the $, and you can use this to just mute outputs. So let's assume you have you're looking for a bunch of compounds. Let's say anything that has egap 0, so anything that has a 0 band gap and 4 species. Every single result you will get back will have n species 4 and egap 0. That is kind of a waste of space, because you already know from your query that n species is 4 and that egap 0 for all of them, because that's how you set it. But if you put, I can just show you how that looks like. Here, egap 0, n species 4, egap 0, n species 4. Is there a string wildcard? I can't get any question. Is there a string wildcard like in Bash? All you do is start with AFLOW 5b. We don't have that yet. No, we don't support regular expressions. That would be really cool if we could, but we have not implemented regular expressions yet. Good question, though. Any other questions? I really like the questions we're getting here. They're really good. Okay, so we see EGAP here is 0 for all entries and SB is 4 for all entries, and this is not particularly exciting. So we can use the mute operator to suppress this output and save some bandwidth and save some space if we want to store all these JSONs somewhere. You see, this is all gone with the mute operator. We can also mute default properties. So if you, for example, don't care about the, let's say the AUID, you can just add those and they will not appear. You can just add it with the mute operator and they will just not appear in the final result. You see there's no AUID anywhere. You can do this with any property. Any questions on the matchbook? This is really all you need to put this together, and the rest is just knowing what properties you're looking for. Okay. So something that I've not really been telling you is that it says we have entry 2 out of 1,133. But when you actually count the results or go to the end here, you only get 64 back. And that is plain and simply to save bandwidth and, for example, save your browser, because your browser can only handle really so many entries at a time. But that's what we have the paging directive for. Paging directive can be used to go through different pages. We have default of 64 entries per page. So paging 1 will return the first 64 results. You see we start with paging 1 and we will end, if we scroll all the way down to 64, it will not go any further. If we do paging 2, we will get the next 64 results. You see it ends with 128, and if we go all the way back, the home button, of course, doesn't do what I want it to do. If we scroll all the way back, we will end up with 65. So can we change the size of the page we get back? Yes, we can. If we use paging, let's say 1,100, we will get 100 results back per page. Here you see it's entry 1. If we go to the second page, it should be entry 101. So this is how you can determine or can tell AFLUX how many results to get back. So if you want to return results in batches, you can just go through the pages. Another way to return what paging is for is by using the mute operator. Let's go back to paging 1. And you see we get this kind of JSON-like return, but you can also return it as an array if you are more interested in array by using the mute operator. In front of it, you see this is an array. There's no key anywhere. It's just a regular array that you can loop through. So now if you're not interested in paging, if you just want everything back, there is the directive paging 0. This is fairly harmless when you're doing this in a Python script. But if you do this in a browser, be very careful and know what you're doing. With 3,000 results, your browser is probably going to handle it. But if you are returning 3 million results, your browser is probably going to crash. So really, really be careful of using paging 0 anywhere that is not a Python script or any kind of other script that you're writing. Paging can also be used to sort results. So paging 1, again, when you're looking at the band gap, you see it starts sorting in ascending order. but if you use paging -1, it does it in descending order. And of course, you can combine it with a page size. So -1, 5 will return the 5 highest, largest results. Here we'll do the 64 highest, and you can see it's sorted in descending order. And it also works with 0. It might look a little weird if you write paging -0, but it actually works. You can do 0 and -0 to sort. And another thing to keep in mind is that everything is sorted by the first property. So it looks like I forgot to copy this over. So here, when you put EGAP first, it sorts by electronic band gap. But if you add a property called like spin atom, and don't forget to add the paging -1, you see that it actually sorts by spin. And it only sorts by the first property. It doesn't do complex sorting like first EGAP, then spin atom, and only first spin atom and then EGAP. It only does the first. Almost done. The last thing I want to introduce you to are aliases. Let's imagine we want to look for a zinc blende compound, which consists typically of a metal and a chalcogen. So if we were to just type out all the elements, this is how that query would look like. Oxygen or sulfur or selenium or tellurium and every single metal here. If we wanted to have a broad search, this is an absolute monstrosity of a query, but it works. So, but nobody wants to do that. So what can we do to make this more palatable? In the search page, we had these metals, alkali metals, and you can use them as if they were an element. And you can do the same thing with AFLUX. Here you see all 350 results. You can do the same thing with AFLUX. AFLUX supports the same aliases. Instead of having this huge string full of elements, we can also write chalcogens and metals, and you will get the exact same results. And these are the aliases we have. They are the same as on the search page. So if you're unsure about these aliases, you can just go to the search page and click on these buttons, and you see exactly what those are and what elements they belong to. So you see we have 350 results. Here we also have 350 results. They're exactly the same. So they're quite handy if you have a broad search with a lot of different species. Any questions on the paging directive, sorting, or the aliases? If not, we can go maybe into now it's probably better to get into the breakout rooms to do the exercises. The first one should look familiar. It's the same one that we had in the search page. And yeah, maybe try and get 1 or 2 exercises done. Okay, I hope you got at least to do 1 exercise with AFLUX. I'm presenting the first one because that's what I got to do in my breakout room. And yeah, we want to look inside the ICSD catalog. So we need to add catalog ICSD for AL bulk moduli. So we add AL bulk modulus VRH with the star because we want to actually find bulk moduli, not just entries, not get any null values. Species is titanium, so because we have materials containing titanium. And you want to add the Vrh lattice, relax, and EGAP type. And the other important operational sentence here is, what is the material with the highest bulk modulus? So we put the bulk modulus at the very first position, and we want the highest. So paging needs to have -1. And because we only want the one with the highest bulk modulus, we can also add 1 as the page size, so we only get the one with the highest entry. And we see iridium 3, titanium 1, which is the exact same compound that you saw when you used you get the same exercise with the search page. You get the same bulk modulus. Broadly lattice relaxed. Broadly lattice is simple cubic, and E-gap type is metal, and that's exactly what we found before. The next one is determine the bulk moduli of all binary materials with a transition metal and chalcogen. Band gaps between 1 and 3 electron volts. And we want the compound with the lowest bulk moduli. So again, we are using AFLOW Bulk Modulus Vrh at the beginning because we are sorting by bulk modulus. E gap is 1 star, what's between 1 and 3. What else? They are binary, so n species is 2. And species here is transition metals, chalcogens, and yes, that's it. So we want the ones with the lowest bulk modulus. So paging is going to be +1, sorting ascending, and page size is 5, just to limit the number of results we're getting back. It's really interesting. The 5 lowest, and we see there's some hafnium sulfide, molybdenum selenide, tungsten sulfide, manganese telluride, and this is how we get the 5 lowest. So now we want to narrow down the choice of transition metals to iron and nickel. So species, in this case, iron, nickel, or cobalt, and the chalcogens. We want the one with the largest magnetic moment per atom, so spin atom has to get to the front. Chemical formula, space groups, bulk moduli, magnetic moments. So we want a AL bulk modulus Vrh in there, and I guess n species 2. Directive paging. We want the one with the largest magnetic moment, so -1, and we again only want 5 compounds. So paging -1, use the mute operator, so we get an area back. And we see there's some iron oxide, cobalt oxides, another cobalt oxide with a different space group here. It's 2216, and it's 186, nickel oxide and nickel sulfide. Any questions on the exercises? It's really all about which properties do you want, how do we limit the properties, or which properties can we limit, and which one do we want to sort by, and how do we want to sort them by. These are really the 5 questions that you need to answer, and the rest is really just knowing the property names and knowing your own parameters. If there are no more questions, I want to take 5 minutes to show the so-called REST API. We have REST API. Okay, you've seen all this time. You can check here. There's a so-called AURL, and I've not explained at all what this AURL is. And the AURL can be converted into an actual URL by replacing this colon with a slash. And when you follow that link, you get to an API like this, which has the properties that were calculated for this particular entry. This is essentially our entry page, but it's formatted a little more primitively, a little more simpler. That's not the only thing that it does. You can actually query that particular REST API. You can query that page, which you can't do with a nicely formatted entry page. So let's, for example, query egap. And you see that this particular iron oxide has a band gap of 0. We can verify that by plain and simply looking at it. Here. egap is 0, and you can query this property here by plain and simply adding the REST API, question mark and the property at the end, in this case egap that we're looking for. We can also look for anything else, spin atom, and we get, should probably also change the property name for printing purposes, and we get these results. So if you have an ARL and you're looking for a specific property, you can also do this programmatically with a REST API. And this has a very nice side feature because you can also access certain files, like our output file, if you're interested in downloading a structure, for example, to input it into a machine learning model, into our machine learning model, which we'll talk about tomorrow. You can do this by adding this concar relax file at the end. So this is the, I can show you here. No, not here. There's a browser within a browser. You see we have a files property, and these are all links to. And if you keep going through this, you see the concar relax file. And this is exactly the same one that you can query with a REST API. So in summary, I'm going to go back to my slides. I've shown you some in more detail than others for the 2 ways each how to access our data. We have a graphical user interface with our search page, and we have an application program interface with AFLUX to look for data and to filter data. And we have a materials entry page and a REST API to actually look at a specific entry and look for specific properties, depending on what you are looking for and how you want to access it, either just briefly checking using a GUI, or if you want to access the data more programmatically, we have the tool for it for your needs. So with that, I will take any more questions about anything. I really enjoyed the questions today. Some of them are very, very good, very creative about what you want to do with AFLUX. Doesn't look like there are any more questions. So with that, I'd like to thank you for your attention and for your very good participation. And I'll see you all tomorrow. I think thermodynamic stability is first, or thermomechanical properties, one or the other. But
I think thermomechanical properties is first.
Professor Cormac Dorr is going to start tomorrow with thermomechanical properties, and I will